Hi class. So today we're going to be looking into how can we analyze model performance, right? I think that what this class is mostly going to help us with is to understand better what are the different types of parameters that we can use to understand how well our prediction or our classification is working, okay? We've seen so far several measures. We've talked about accuracy for regressions. We've talked about precision and recall for classifications. But today I'm gonna give a broader overview of the different features that we can look into. And so as I was saying, we are mostly going to cover how can we measure and report performance results for binary classification and multi-class classification. And we are also going to be looking into something called ROC curves, which also allow us to understand how well our classification is working. And we'll also talk about cross-validation. That's something that you have informally been doing as well. Which is basically how do you divide your data set into training and testing. And so cross-validation, it's basically going to allow us to understand different ways of dividing the data set into training and testing, depending on the type of data that you have, depending on the size of the data, and so on. So we'll be discussing that. And then on a second part of this class today, I'm going to be talking about the caret package, which basically allows you to compute and compare the performance of different classifiers. So far, you've been doing that informally by basically comparing the output of different commands. What the caret package allows us to do is to formally understand how different techniques compare by using exactly the same training and testing data sets, exactly the same number of repeats, and different techniques for those data sets. And so let's start with performance measures, right? And so we've talked already about what confusion matrices are, right? And that's something that you have been using so far in many of your results and homeworks. And so basically, this is a setting in which we have a problem based on classes. Okay, this is again a classification problem. We are not talking here about predictions. Remember that when we work with predictions, like for example linear regression, we try to predict a numeric variable. In that case, what we can report are things like, for example, what's the correlation between the actual values and the values that our model is predicting, or we can report things like, for example, root mean square error, right? Here I'm going to talk mostly about performance measures for classification settings. And so the simplest classification setting we could think of is the binary classification, right, in which we basically have a problem with two different labels. So for example, predict whether a sample from a given individual could be a cancer related sample or not, right? And so the positive would be correctly predicting that label, the negative would be incorrectly predicting that label, right? And so what a confusion matrix represents is basically, on the one hand, you have the predicted label, that's the outcome of your classifier, and on the other hand, you have the known label, right? Remember that this is always a classification setting, and it's supervised. This means that every single data point in your collection has a label. And so what we can say is how many times, whenever our classifier predicts something, how many times are we correctly predicting it, right? It will be the positive. Basically, it's the positive and positive. So what's the true positive rate, right? Whenever we predict something as positive, but in reality that's negative, that's a false positive, okay? Whenever our classifier predicts something as negative, but it's actually positive, it's a false negative. And then if it predicts it as negative, and it's a negative, and the ground truth label is negative, it's called true negative. Okay, remember again that this is the setting for a binary classification. And so these different measures, the way different performance measures are computed is basically using the true positive, false positive, true negative, and false negative values that you've seen in the confusion matrix, right? So basically, looking at the confusion matrix, there are different things that we can compute that are going to tell us how well our model is doing. And those measures, the measures that I'm going to be talking about today, are precision, recall or sensitivity, specificity, and accuracy. Okay, some of them you're already familiar with them in the sense that you have been using them, but maybe you weren't fully aware of how it was computed. Okay, Let me clarify as well that although you can, I mean, as an exercise at home, you can basically try and see, okay, given a confusion matrix, can I let me see and compute my own accuracy and my own recall and precision and see if, you know, those numbers are correct. You can do that manually, but we will be seeing today how there are packages in R that allow you to compute these performance measures automatically. Okay, and for example, that's also something that the CARIT package does. And so if we go through these measures, so what's precision? So precision, you see there that it's computed as the true positives divided by true positive plus false positive. And so it's basically defined as the percentage of positive predictions that are correct. Okay? Recall, it's defined as true positive divided by true positive plus false negatives, and it's the percentage of positive label instances that were predicted as positive. Okay? Specificity is the percentage of negative labeled instances that were predicted as negative, and accuracy is basically the percentage of predictions that are correct. There are basically two different ways of right? So there are those measures that take into account the total labels as outcome of the classifier, right? So how well is our classifier doing in terms of, you know, comparing the labels of the classifier with respect to the actual labels, right? And there's something else, which is with respect to the known labels that we have, how well is our classifier recognizing those known labels, right? And so something like precision is heavily focused on measures from the predicted labels. Something as recall is heavily focused on known labels. Let me clarify this further. If we look at this matrix, what you can see there is that the way, I mean, what you see here, the arrows indicate what are the features that we are using to compute each of these four measures, right? And so what you can see is, for example, is that the precision basically uses true positive and false positive rates, okay? What this means is that what precision is trying to understand is from all the labels that have been predicted by our classifier, how many of them are correct, in the sense how many of them replicate the known labels. Okay, that's what the precision is representing. Whereas if you look at something like the recall or the specificity, basically what those are doing is basically understanding how many samples our classifier is being able to identify from the positive known labels. Okay, so from all the positive cases that we have, how many of those known positive labels is our classifier being able to identify? That's what recall is, right? And so that was what I was trying to say before, is that, you know, a measure like precision is heavily focused on what are the predicted labels that we have, okay, and how well we are doing, whereas a measure like, for example, recall or specificity is heavily focused on these are the known labels that we have, how well is our classifier doing in terms of identifying the positive labels in our known data set. And then the accuracy, it goes like a diagonal arrow. It's basically a mix of both, right? The accuracy is telling us, okay, from all the different cases that we have, you know, the ones that we predict based on the known labels, how well are we doing overall? In general, when we look into those measures, right? I mean, so when we have a classifier, what is it that we need to report? Do we need to report only the precision, only the recall? Do we need to report the accuracy? So, you know, in general, I always recommend report all of them, okay? All of them are telling us a different story of the data, right? So the recall is telling us how many positive samples can we extract from all the known labels that we have, right? The precision is telling us how well are we doing for those for which we say something, how well are we doing, right? And so it's telling different parts of the story. And also something very important to take into account is that oftentimes if we only report accuracy, right, that might be giving us a misleading information, because in fact, imagine the case in which you have 90% of the population that does not have cancer, 10% of the population has cancer. And imagine that 10% of the population is absolutely misclassified. Like, we are not able to identify a single case of cancer. Okay? The accuracy of our model would still be 90%, because in fact, for the ones that do not have cancer, we are able to identify them. Right? And so the accuracy basically tells us a global story. Accuracy is measuring how well are we doing overall for both positive and negative cases, right? But chances are that we are probably more interested also in understanding how well are we doing for every single class, right? So that's the reason why reporting things like precision or recall, okay, how well are we doing for the cancer cases? How well are we doing for the non-cancer cases? How many of those cancer cases are we retrieving out of all the cases that we have? I mean, understanding all these different nuanced measures give us the whole picture. And so in general, my recommendation is basically report as many performance measures as you can and make sure that you explain what each single performance measure is telling us about how your classifier works. I mean, basically, we've seen the binary classification, right? I mean, if we go ahead and think of cases in which we have more than two classes, for example, the example that I'm showing here has three classes, how good a confusion matrix look like, how good those performance measures look like. So they could look like very similar to the ones that we've seen for the binary case. What I'm showing here is a scenario in which, the gold labels, that's another way of naming ground truth, gold labels, right? Those are the known labels. And then the predicted labels are the labels that our classifier is outputting, right? And so what we see here is that, we have a scenario in which our classifier is able to predict basically like of the total gold labels A that we have, which are 100, okay? We can predict 30 of them as being gold label A, okay? We can predict 60 samples that have label B as being B, and we can predict 80 samples that have label C as being label C, okay? So by looking at this confusion matrix, right, if we look at the diagonal, which is telling us, how many samples we are predicting for each of the gold labels that we have, basically we can say that, this classifier is doing really well for label C, okay, because we are able to basically, predict most of the cases that actually have a label C, right? But we are not doing so well for labels B and A, right? And so what you see there are the totals are representing two different points of view, right? So the total gold labels are representing the total known classes that we have. So we have, 100 different samples with label A, 100 different samples with label B, and 100 different samples with label C. Okay? And then the total predicted is representing the number of samples that our classifier outputs as being A, B, or C. Okay? So we have, in fact, 100 samples in our dataset that have label A, but our classifier is only determining that 60 samples have class A. Okay? Or, for example, we have 100 different samples that have a gold label C, okay? And our classifier is able to capture 80 of those. And so, given this example, how is it that precision and recall is computed for such a setting, right? And so the answer is that, the computation is very similar to what the binary case looks like, but basically expanding it to multiple classes. So let's compute the recall. I mean, what this example is going to show you is going to walk you through the computation of both precision and recall for each of the labels that we have, okay? Again, remember that the recall is the true positives divided by true positives plus false negatives, okay? And the precision is true positives divided by true positives plus false negatives. So the precision is telling us, how well are we doing in terms of, predicting label A, okay? How well is our classifier in predicting label A? How good is our classifier in predicting label A? And then the recall is telling us out of all the labels that we have, out of all the samples that we have with class A, how many are we recalling? How many is our classifier able to retrieve? Okay, that's what recall means. You might have a really high precision, but a very low recall. And what this means is that, we are not able to say something about many samples, but for the samples that we can say something about, we are very accurate. And so if we look at this example, I mean, you can go through these numbers yourself, but basically for the recall, what you see there is that the true positive that you have in there for label A would be 30, because in fact, those are the labels that our classifier is labeling as gold label A, and in fact, they have label A, okay? And it's divided by the total number of gold labels that we have. Again, remember that what recall is representing is out of all the label A's that we have, how many data points is our classifier able to retrieve, to say something about them. And then the precision, what the precision measures is basically, in terms of the classifier itself. So if the classifier predicts a label, a data point of having label A, what's the precision of that prediction? Like, how confident can we be that that prediction is correct, right? And so in that case, you need to divide the true positive, which is again, the 30 data points that we have, divided by the total number of instances that have been predicting as having label A. So this would be 30 divided by 60, okay? So the precision in this case is pretty low, it's only 50%, okay? You can repeat exactly the same thing for B and C, okay? It's exactly the same reasoning. So we can see, for example, for label B, that we again have a really, average precision. It's only 50%, but the recall in this case is slightly higher, okay? So we are saying more things about data points that have label B, and that's what the recall is saying, but the precision is not that good. So besides precision, recall, sensitivity, specificity, there's sort of a measure that embraces a combination of those, and it's called the F measure. Okay, so typically when we have the scenario that I was talking about before, in which we have, say, 90% of the cases are non-cancer and 10% of the cases are cancer, I was saying, the accuracy is just not gonna explain, it's not going to explain the whole picture, and so we need to report things like precision and recall. That's perfectly fine, but we can also report a combination of those, and that's what the F measure does. And basically, this formula here is what how the F measure is represented. And so sometimes in order to be able to compare classifiers, it's also interesting to report F measures. The F1 measure is also known as F1 score, and it can also be computed in multi-class settings. The way most of the packages do it is by taking a one versus all approach, whereby basically one F1 score is computed for each of the one versus all combinations that we can compute. For example, if we imagine a setting with 3 different classes, we would compute 3 different F1 scores for the classifier that identifies whether a sample is of class A or not when compared to classes B and C, for a classifier that identifies whether a sample is of class B or not, being the others A or C, and for a classifier that identifies whether a sample is of class C versus being of class A and B. And of course, if we are computing this type of F1 score measures in multi-class settings, we can compute one F1 score for each of these different classifiers, but sometimes most of the packages also compute an average across the different F1 scores. And that average can be computed either as a macro average, which is just like the average of the F1 scores that you have computed for each of the classes, but it can also be computed as a micro average. And the micro average, what it does is that it takes the actual true positive, false positive, and false negative across, all the different settings. And this is done so that we can account for the actual number of samples that we have per class. Micro averages are mostly used in cases where we have imbalance settings. And let me walk you through an example so that you understand the difference between macro and micro averages. I have simplified this example so that we are only computing precision instead of F1 score, but the reasoning would be the same. So in this case, we have 4 different classes, A, B, C, and D, okay? And when we build the one versus all classifiers for class A, C, and D, we have one true positive and one false positive, okay? So the number of samples that we are working with for classes A, C, and D is much lower than for class B. For class B, we got 10 true positives and 90 false negatives. And so you can in fact see that the precision for A, C, and D is 0.5. It's quite high, whereas the precision for B is much lower. Now, if we compute a macro average, then the precision could be just the average of all the precisions that we have divided by 4 and could be 0.4. But if we compute a micro average, the micro average could use the actual true positives and false negatives for every simple class globally looked at. So we would have 1 plus 10 plus 1 plus 1 true positives divided by the false positives plus true positives for each of the classes, which are 1 plus 1, 10 plus 90, 1 plus 1, and 1 plus 1. So you see in the denominator, it's 2, 100, 2, and 2. And so by computing that new precision, the micro average precision could be much lower than the macro average. Okay, so basically when you have cases in which these are imbalanced settings in which one class has a much larger number of samples, it's highly advisable to use micro F1 scores that will reflect better the reality of the results that you